This video is going to do a quick introduction into how the CFD simulations were performed for this thesis study using ANSYS Fluent. So, to give a quick summary, we have this settler tank, this spent litter settler tank with incoming spent litter flowing into the central feed well, and we're going to simulate that spent litter both surging through the bottom of the feed well and into the rest of the outer tank area, and sloshing over the top of the feed well to investigate what sort of wave propagation occurs from this resonant inlet pumping. So, starting our ANSYS Fluent model here, you can see we've got our geometry, mesh, setup, and solution options, which we're going to go through in the following videos, starting in the geometry design modeler. So here we've jumped straight into our design modeler to create the geometry that we're going to use in our simulation. So I've made this 2D sketch here on the XY plane, and you can see all the different sketch dimensions down here. It's 17 meters radius of our tank from the central axis to the outer wall. And you can see that the feed well is 3 meters radius and 3 meters tall, and all these other dimensions listed down the bottom here for your reference. Once the sketch was made, I created a surface from sketch using this tool, and that just created a single surface from this outer perimeter line, which we then used this face split tool to separate that single surface into these 3 different areas using the geometry of the sketches. And now that we've got these 3 different surfaces separated, I used the name selections. So by right-clicking and selecting name selection, you can name each of these sections, which we can see down here. I have the air region, the fluid region with the high-density SPL, and the feed well region, which is where our incoming low-density air-rated SPL is going to be entering the system. Also name some of the different lines and boundaries, like this central wall axis. I have the inlet and outlet, so the inlet into the feed well and the artificial pressure outlet we've created at the bottom here. And it's important to name these inlet and outlets so that they're automatically recognized as such in the setup phase. I also have the tank wall named, the boundary between the air region and the fluid region, the bottom of the feed well, the walls around the air region, and the feed well walls here. So while not all of these names are entirely necessary, having thorough name selections definitely makes it easier later on when you're doing your boundary conditions and even with meshing to be able to identify what the different options are in the settings. So this summarizes everything in the design modeler for our geometry input, and now we're going to look at mesh. Now we've opened up our mesh editor, and you can see the geometry we've created has come through here, this 2D planar model with the 3 different surfaces that we've named in the previous section. All of our name selections which we made come through here and are identifiable just by clicking on them, and now we just need to enter some mesh controls and generate the mesh. And for this sort of a model, just a 2D simulation, it's fairly straightforward to do the meshing. I've got one mesh sizing option here where I have selected all the edges. So if you right click on mesh and go insert sizing and then select all of the edges individually, holding down control, we can put that geometry into this mesh sizing setting, and with no bias we're just going to set that element size to 0.15 meters, which gives us a pretty good resolution here, yielding good residuals and simulation convergence, while not being over the top too intensive. Because this is a transient simulation, the mesh isn't as fine as you might make it with a steady state simulation, just because there's so many more iterations in total that have to be performed. It becomes quite computationally expensive. So after generating this edge sizing control, we've also added a face meshing option where we've just selected these 3 faces under mesh, insert face sizing, face meshing, sorry, and applied that. And once we've generated our mesh using this button, this is our final output, which is of high enough resolution for this sort of simulation, and it's not too computationally expensive, although the computer I'm working on was having some troubles with the transient simulation. So this concludes the meshing setup for our simulation, and next we're going to go on to the setup phase. Now we've opened the setup application of ANSYS Fluent, and to save time I didn't show opening this, but we did enable double precision and change the number of solvers to 4. So in the general setup we have a transient simulation we've selected, and we've also changed the gravity to minus 9.81 meters per second squared in the negative y direction. So our first model that we've enabled is a multi-phase model. Since we have 3 different fluids interacting, we've got the air, the low density SPL, and the high density, the low density SPL in the feed well and the high density SPL in the surrounding tank region. So this multi-phase model, we've got a homogeneous volume of fluid model enabled with 3 Eulerian phases, and none of these other options have been changed, and we've set up our 3 different phases here and named them accordingly. We've got air, SPL, and SPL aerated. And in the phase interactions tab, we've set the surface tension coefficient between the 2 liquids to 0.04, and between the liquids and air, we've got them set at 0.07. So that concludes the multi-phase model setup, and next we have the viscous model setup, where we've enabled the K epsilon model with standard settings, but scalable wall functions have been enabled as well, and we haven't changed any of these model constants. Next we have our materials setup. So these were selected in our for our 3 phases, and we have air, which was just one of the materials driven by the Fluent database, and we've also got the SPL and SPL aerated fluids set up, which the material properties of those were given by some process engineers on site. Our cell zone conditions were automatically defined, but sometimes you can have zones appear as solids instead of fluids, and if that's the case you can change that by changing the type here to make sure they're all fluids, and all of these are mixtures. In our boundary conditions, if we change the view, we can see our inlet and outlet have been already defined automatically because we use the name selections properly. And for our velocity inlet as a mixture, if we go into the boundary condition settings for this, we've changed the velocity magnitude for the inlet to 1 meter per second. And if we go to the aerated SPL stage, we've set the volume fraction of this to 1. So what that does is it makes it that only aerated SPL is entering through this inlet, and there's no higher density SPL or air entering through. It's only this one phase entering through the inlet. We have an artificial pressure outlet that's been set up at the bottom as a mixture. And then the only other thing we've had to do, there's been no changes to any of the walls, but the air fluid boundary and the feed well bottom, so there's this boundary here between the air and the SPL, and the feed well bottom, which is a boundary between the central feed well and the fluid region. These were originally populated as walls, and we've had to change the type to interior to allow fluids to be able to pass through those 2 different interfaces properly within the mixing. So that concludes the boundary conditions, and that is our setup. There's no dynamic meshing or anything, just the standard meshing options we've used earlier. And in the next video we'll talk about the solution controls. Now that all of our simulation setup options have been configured, we can look at the solution, and the first thing we'll look at is our residual monitor. And here we've changed the absolute criteria to 1 times 10 to the minus 5 for all of these. And while these can be lower, because we're doing a transient simulation, there's so many iterations that are being performed in total, we're probably not going to reach these residuals as it is, and that's just because this computer I'm working off of doesn't have the computational power to be able to solve that many iterations across that many different time steps. So this is sufficient for this sort of simulation, regardless. And then the next option we need to look at is the initialization of the solution. So we've done a hybrid initialization, and after we initialize the simulation, we can go ahead and patch it. So patching just here we're going to select aerated SPL, volume fraction, set that to 1, and we're going to make sure that the volume fraction is 1 for the SPL aerated in the feedwell region, so that's making sure that initially this feedwell region is filled only with the aerated SPL, so we'll select patch, and then we're going to select air, volume fraction 1, and we'll patch the air region, so everything in the air region is air, and there's no aerated SPL or SPL. And then the rest of the system, which is just the fluid region, will be set with our default fluid, which is our regular SPL, the high density SPL. So now that that's patched, it's properly initialized and ready for our solution, but there's one more thing we need to do, which is set up our calculation activities. So ignoring animation 1, I've just used this animation here, called animation 2, and it's recorded after every time step. And if we look at the contour I've used, named contour 2, it's just a contour of the phases, and it has the phase ID in the legend. So this is just going to show the 3 different phases interacting transiently throughout the simulation, and that's just selected the 3 different fluid regions here with smooth coloring. If I show that, you can see we've got our air, we've got our aerated SPL, and our regular SPL here. So that's our animation defined, and now we're ready to run the calculation. I've used 150 time steps at 0.2 seconds here, which gives us a 30-second simulation, and I've used a maximum of 20 iterations per time step. This is purely constricted by the computational power of the computer I'm working on. Ideally, we'd be able to increase this a fair bit more, but as it stands, the simulation takes a very, very long time to run and has encountered errors with higher iterations per time step. So that concludes our setup and solution settings for the simulation, and next we'll talk about the results. Now I've clicked calculate, and we've run our simulation, and we've gotten the animation results which we asked for. The console shows all the different residual values throughout the simulation, and you can see it completed successfully with no floating point exceptions. We can view our scaled residuals here. It shows we went through just over 3,000 iterations, and our residuals hovered between these ranges here. Ideally, we'd have these a little bit lower by using more iterations. As you can see, they are starting to converge, and I have done a convergence check if we do use higher iterations. But for the sake of these simulations, this will be sufficiently accurate, and we are conserving computational power, even though this takes nearly an hour to complete in total. So if we go to our results down here, we can look at our animations and select playback, and that gives us animation 2 is what we were looking at, which is our phase ID mixture. And here we can look frame by frame at what the simulation does, and if I change the playback speed Scroll it down a little bit. I can play this animation and see exactly what happens. So this shows how the aerated fluid leaves the central feed well, and because it's of higher density, it rises to the top against gravity, and creates surface waves in the outer cellular tank, and how the waves propagate and interact with each other over time. So this simulation you can change the speed and get it exactly how you want it, and you can actually write this to a video file, selecting video, and you can save animation that way, or alternatively you can play it through here and screen record this section, which actually gives you a little bit more flexibility with how the video is going to end up looking. So that is our results completed. This animation is the key thing we were after, and we've also got our residuals there for confirmation. And that concludes this tutorial on how the setup was completed, and how the CFD simulations were completed, and all of the methodology and different parameters and setup options which were a part of that.